Ooh, 29 people in the waiting room. That's exciting.
Okay, we are now live.
Excellent. Can we start admitting people? I'll probably give it till 5 after to start, just to make sure that everybody can get in.
Sure.
Hello, everybody that's joining us as you're coming in. I just want to let you know that everybody's going to be muted for this presentation. So you're muted as you come in. Don't stress about it. It's all going to be easy peasy lemon squeezy once we get started. Just give us a few more minutes so we can get everybody in that has signed up. We've got a lot of people coming today. Really excited to get started. Hi guys coming in. If you didn't hear me already, you're all going to be muted today just because we've got a lot of people coming in. So pay no mind to that. If you have any questions, you can ask them in the chat. Those are all listed as private, so those should only be going to the host. So we'll be keeping an eye out for those.
Hi all.
It's always awkward when people are on mute. Hello, I'll wave.
It's great to see you all though.
No, I'm so excited. Thank you everybody for joining us. I can't wait. I'm just here to enjoy the presentation personally, so that's the only reason I'm here. Just give us a couple more minutes, guys. We're waiting on a lot of people, so we want to make sure everybody gets in before we get started. All right. Thanks, guys. If you're just getting in, we're going to get started in just a couple of minutes. I see people joining, so I think there's still some people in the waiting room. Sit tight. We're going to get started in just a moment. Okay, just give us one more minute, everybody. We might have some more stragglers joining us. All right. I think it's okay to get started now. Anybody that comes late, we'll just jump right in. Hello, everybody. My name is Natalie, and I am the office manager for Tumblehome. I'm going to be moderating the session today, so just a couple of quick things before we get started. You may have noticed that you are muted. This is going to stay that way for the entire program. Unfortunately, we don't have time to talk to you all individually because there are so many people joining us today. So you won't be able to unmute yourselves, but if you do have any questions, please feel free to type them in the chat. Hopefully at the end of the program today, we will have a little extra time and we can put our presenters on the spot a little bit and give them a little bit of a ride. So without further ado, I would like to get us started. Thank you for joining us today as we talk about galaxies, planets, and black holes. We are so excited to be joined by Dr. Grant Tremblay and Katie Coppens, who are the authors of this absolutely out of the world book called What Do Black Holes Eat for Dinner? The book itself is remarkable for so many reasons, but I think my favorite part is probably the humor. It's so clever, and it's just a really great way of showcasing that you can be super silly and goofy and smart and still have fun. And it's awesome, and I love this book. It's loaded with these super wacky space questions, and I think that Katie and Grant did an excellent job answering them. I don't want to give too much away because I know Katie's going to talk about this later. So I do want to give you guys something special. I am going to put a link and a discount code in the chat for you guys today that's going to get you 25% off and free shipping on your very own copy of What Do Black Holes Eat for Dinner. And if you don't get that information, if you lose it for some reason, don't worry. We're going to send out an email tomorrow with all of the information you need, so you'll still have that code. So I'm going to go ahead and let Grant and Katie take it from here, and I hope you guys enjoy the presentation.
Okay, thanks, Natalie. Look, you all, Katie and I are so happy that you could join us. We really, really wish that this could be in person. These are really tough times, and we hope that you and your families have been safe and happy and finding joy in these times. Things will get better. And hey, we're here to talk about space. That's going to be pretty fun. Please definitely ask questions in the chat if you do. Don't be shy. We'll try to get to them. I think kids have the best questions about space, right? Kids are great scientists. That's part of what inspired this book, like Katie will talk about. So I'm going to briefly introduce myself. My name is Grant Tremblay, and I'm an astrophysicist at the Harvard-Smithsonian Center for Astrophysics in Cambridge, Massachusetts. So I know a lot of you are on from Maine, so we're only about a couple of hours south. And prior to being at the Center for Astrophysics, I was a NASA Einstein Fellow at Yale University, just a little bit further south in New Haven, Connecticut. And then prior to that, I was an astronomer at the so-called European Southern Observatory, which is headquartered in Munich, Germany, so very far away. And I was also an astronomer at this place, which is operated by the European Southern Observatory, which is the very large telescope. It's called Paranal Observatory in the desert of Chile, about 3.5 hours north from a town called Antofagasta in Chile. So it's in this, highest and driest desert in the world, and it looks like the surface of Mars. And there we've put the world's greatest and most powerful telescopes, because you have 330 crystal clear nights a year and absolutely no water vapor. And so the atmosphere is just pristine, and the stars just are so bright, I swear they cast a shadow. I've known Katie for more than a decade now, right, Katie? And I'm so lucky to know Katie because she's the best children's author I know. I have never written a children's book before. So this is a totally new experience. And this book was Katie's idea because Katie is also, in addition to being a great author, a great teacher. So she'll introduce herself. But it's just, I'm really happy to be involved in this, but I've just been along for this ride with Katie, and Katie's really the star of the show here. So go ahead, Katie.
All right, well, my name is Katie Coppens, and I am a teacher. I'm currently a 6th grade teacher at Falmouth Middle School in Falmouth, Maine. And I've taught everything from 3rd grade all the way up to high school over the years. So teaching is definitely my passion, and it's also become a piece of my inspiration as a writer. So Grant's going to go to the next slide, which shows some of the books that I've written over the past few years. The very first book I wrote, it's the blue one that has the light bulb with the pencil, was actually for teachers. This is for the National Science Teachers Association, and it's called Creative Writing in Science, and a way to help teachers integrate science and literacy, specifically around different writing topics. And from that, I'm a columnist for NSTA, the National Science Teachers Association Science Scope magazine. So I get to write columns about kids and teaching and how to get more writing and science combined. And with that, over time, I just took inspiration from my students to come up with topics that I thought would be interesting and fun for them in books. The first kids book I wrote is for Tumblehome Books. They're the publisher of it. It's called Geology is a Piece of Cake. And this is one that teaches all kinds of geological concepts, ranging from rocks and minerals and fossils to even some space in there, and comparing it to cake and cake recipes. So there's actually some fun recipes throughout it. And then that led to, for Tumblehome, a companion book called Geometry is as Easy as Pie. And so in this book, you get to learn a lot of math facts by comparing it to pie, and there are also pie recipes throughout it. I was also an editor of a book of poetry for Tumblehome called 7 Stories About the Moon and 100 Other Science Poems. I also have a couple of poems that are in that book. Another series that I have that I'm known for is called the Acadia Files. And this is set over the 4 seasons, and Acadia is a 5th grader who lives in Maine. And in each chapter, she learns a different science concept. And it's full of her questions, and every chapter ends with her science notebook where she draws pictures of what she's learned. So a huge passion that I have is teaching kids through reading and writing and trying to make everything really fun. Learning should always be fun, and that's my goal in these books. And I hope you have fun with us today.
Katie's books are awesome. Just a plug, go pick them up. So yeah, I don't really write books. I do research, and so I write these really boring, dry papers. I have done some stuff for the public. I'm a regular cast member, regular on these 2 documentary series that are on the Discovery and Science channels. One of them is called Space's Deepest Secrets, and it's airing now at the new season is airing now on the Science Channel at 9 p.m. Eastern time on Tuesdays. So we're just started the season. And then How the Universe Works, I also do every year. And I think the new season is coming out in the winter. But anyway, these end up on Netflix at some point, so keep an eye out for those. I have written 1 book for the general public besides the book that we wrote with Katie. But this is more of a picture book, a coffee table book. As part of my job, we operate the Chandra X-ray Observatory for NASA. And the Chandra X-ray Observatory is one of NASA's great observatories. It's been in space for 20 years, and we just celebrated its 20th launch anniversary. This was the heaviest and largest payload ever launched by the space shuttle in 1999. And it's one of the world's most powerful space telescopes by far. It's the most powerful X-ray telescope in the world. And our book, Light from the Void, really celebrates its scientific accomplishments over 20 years.
All right, so a big question is, why did we write this book? So this book has a pretty silly title, right? Like, what do black holes eat for dinner? And that's what the book's all about. It's about having fun with asking questions. So as a teacher, that's what makes it so fun for me, is seeing the things that kids ask and encouraging them to be curious and wonder why and really think deeply. A huge part of this book, the majority of the questions actually were generated by my students, which was really fun. And I asked them to think outside the box. Think of questions that you can't just Google and find the answer, right? Like, not questions like, how big is Jupiter? Think stranger, think odder, think sillier. And they absolutely did. And that's what this book is filled with. And I think what makes it so great is the questions seem silly on the surface, but that's the title. They're actually super smart. And there's a whole lot of depth to what they're wondering. So our text structure for the book is actually a giant conversation back and forth between a student and an astrophysicist. So it's just a conversation, and it goes in a whole lot of tangents in different directions. Throughout it, there's so much science packed into it for these questions that seem really light and silly, and you'll see many of them in this presentation. Because it's so heavy in vocab, we have these little vocab bubbles throughout it. So the next slide is going to show you just the layout of it. So we have these amazing pictures, which are public domain from NASA, that we got to use throughout the book. And you can see it truly is question and answer. And the questions, like I said, just kind of go all over the place. And it's a book that's fun to just sit down and read one question and one answer, or you can sit and read the whole thing, because it truly is this back and forth conversation. And Grant and I had a lot of fun getting humor in the book. We thought it would be a way that we get kids engaged and excited about the book. And you'll see a little bit of humor in this presentation today. So we wanted to start with our first question, is a pretty big one. How big is our galaxy? So our galaxy is the Milky Way. And the image you're going to see is one that we see quite a lot. So this isn't the Milky Way itself. It's a different galaxy, but it's similar in size and shape to the Milky Way. And often we hear this size, right? The Milky Way is 100,000 light years. But what does that actually mean? And so for that first question of how big is our galaxy, I'm going to get to a fun way to teach you the answer. But first, Grant's going to give you a little astrophysicist background on images of galaxies.
Yeah, so we think there are about 2 trillion galaxies at least in the known universe, right? And a galaxy is a big swirling vortex of about 400 billion stars in some of these largest galaxies, right? We think there are about 200 billion stars in our galaxy alone. And our planet is orbiting one of those stars, our sun, right? Which you can see in the sky right now. But we can't actually take a picture like this of our own galaxy. We can take a picture of literally millions of other known galaxies, but I want you to think about why we might not be able to take an image of our own galaxy that looks like this, right? And you might be thinking that that's because we're inside of the galaxy, right? If you're inside of your house, you can't take a picture of the exterior of your house, right? You have to first walk outside of your house and take a picture of it. And that's our conundrum here with the Milky Way, right? And so when we're talking about the size of our galaxy, it's very hard to actually, visually demonstrate what our galaxy looks like. But this is another galaxy called NGC 1232, and it's very, very similar to what, for example, an alien civilization might see when they look back at our galaxy, the Milky Way. They would see about 200 billion stars in this beautiful grand design spiral that is called a spiral galaxy. Galaxies of many different shapes and sizes. And one of those main shape categories is called a spiral galaxy. So this is actually a painting. This is not a real image of what almost certainly the Milky Way really looks like from the exterior, right? And when you see an image like this, it's really, really hard to imagine the scale, right? So again, there are about 200 billion stars in our galaxy, and our home is situated right at the center of this orange circle here. And so when you go out tonight, maybe you can go out tonight, ask your parents if you can, look up at the sky, and every star that you can see when the sky is really, really dark, right? Every star that you can see in our galaxy comes from this tiny little circular volume here, right? So if you imagine that circle as the cross section of a sphere or a ball, you can only see the stars from within that sphere, right? And so our sun is right at the center of that sphere. It's one of 200 billion stars. We are about 26,000 light years from the center of our galaxy, called Sagittarius A star, where the supermassive black hole, the center of our galaxy, lives. And our galaxy is about 100,000 light years across. Now, what is a light year? A light year is about 6 trillion miles. 1 light year is 6 trillion miles. It is the distance that light, a photon, a particle of light, would travel in 1 year. So it's really hard to imagine from our very limited human perspective how large 1 light year might be, let alone 100,000, right? So we'll try sort of later on in this talk to try to get a better grasp of sort of the scales, but don't feel bad if it's hard to comprehend how vast our universe is, because it is incomprehensibly vast, right? I don't care if you have a PhD in astrophysics or if you're just starting out the first grade. We're both of those people are absolutely confounded by the scales involved. From our limited human perspective, we're just not able to grasp them, and that's okay. So if you were to actually get in a super fast, impossibly fast, sci-fi spaceship and fly to the edge of our galaxy, you might see something like this. And just to keep perspective, if we wanted to actually walk outside of our house to take an image of the house, right, it would only take us a few seconds, right? But if we actually wanted to get in an alien spacecraft and fly out of our galaxy so that we could take an image like this, it would take us literally hundreds of millions to billions of years. So to give you some perspective, the very fastest object that humanity has ever created, which is called the Parker Solar Probe, which is currently in orbit around the sun, it's going many, many, many hundreds of thousands of times faster than the bullet from a gun, right? If you were to actually point the Parker Solar Probe to the nearest star in our galaxy, it's called Alpha Proxima, or Proxima Centauri, that star is 4.2 light years away. So I want you to think, and maybe write it in the chat, how long do you think it would take the Parker Solar Probe just to go from our solar system to the nearest star? And remember, there are 200 billion stars in our galaxy. So the nearest star to our sun, it would take about 47,000 years just to get to the nearest star. So imagine how long it would take the Parker Solar Probe to travel 32,000 light years if it takes 47,000 years just to go 4 light years, right? A long time. So we just can't take an image of like this.
So when I was writing Geology is a Piece of Cake, I wanted to get some space sciences in there. And that whole book is about comparing geological thinking to this analogy of cake. So Grant is my friend. We've been friends for a long time. And I asked him, okay, help me picture the size of the Milky Way, the size of our galaxy. I get that 100,000 light years is really big, but it's so big, it's hard for my brain to picture. But if you're like me, one thing my brain can picture is cake. I hope you're like me. So I asked him this question. I said, if Earth was the size of 1 grain of sugar in a cake that represents the Milky Way, how big would the Milky Way be? And he ran this model, and I don't remember this, Grant. I asked you to double check the fact, and you did double check it for me. And he looked at different size grains of sugar to get the average, to get it exactly right. So picture this grain of sugar in your hand, 1 grain of sugar. Think about how much sugar is in a cake, how much flour, all these ingredients. Picture just 1 grain of sugar in your hand, and how wide this cake would be. That would be the Milky Way. So my hint to you is, look around the room that you're in. It's way bigger than that room. Think about the size of your school. The cake is bigger than your school. Okay, you ready for this? Think about whatever country you live in. It doesn't matter if it's a teeny, teeny, tiny country or a huge country. The cake would be bigger than that country. So imagine this 1 grain of sugar, which is Earth, in a cake that represents the Milky Way. The size of that cake would be 25 million miles wide. So while my brain has a hard time picturing a galaxy that's 100,000 light years, what my brain does know is a 25 million mile wide cake is really, really, really big. And the fact that there are over 2 trillion galaxies really gives a sense of how absolutely enormous our universe is.
So we are just one tiny little rock in this absolutely impossibly vast cosmic ocean. And it's just so hard to comprehend the size. And so I want you to keep thinking about it after we go home, after we're done here today. Keep thinking about the scales of the universe, and keep thinking about our local galaxy, our home galaxy, right? So it's not actually true that we can't actually see our own galaxy because we're inside of it. We can see our own galaxy because we're inside of it, right? So if you actually were to go out, you'd have to go out pretty late for the Milky Way to be up, because it's low on the horizon at the start of the night. But on a really clear night, you might have actually seen this. You see this bright band of light in the sky. So does anyone know what that is? So that is the disk of our galaxy. So remember, our galaxy looks like this, right? So this is like a circular pancake. So now imagine being inside that pancake and looking through the disk of the pancake, right? You can actually see the disk of our own galaxy. This is me, that silhouette of a person. I took this picture. That's me standing in front of the Milky Way at our observatory in Chile. And as the night got darker, the center of the Milky Way, where the black hole at the center of our galaxy lies, was directly overhead. So there's me in the silhouette, and the center of our galaxy, 25,000 light years distant, is right above my head, right? So you can actually see our own galaxy. We're just from within it, so you can't see the whole thing from the outside. But it's still really a spectacular sight. One of our telescopes, called Unit Telescope 4 at the Very Large Telescope, fires a laser at the upper atmosphere to do something what's called adaptive guide star adaptive optics. Artificial guide star adaptive optics. And in this case, we were shooting a laser directly toward the supermassive black hole in the center of our galaxy. So what's cool about this image is that sodium laser, that's really only reaching the upper atmosphere of our planet, is pointed exactly where the supermassive black hole is in the center of our own galaxy. So I can actually show you where that black hole is with a zoom in of real images. So if you actually were to zoom in on this region here, where the, I guess you can't see my mouse, but where the laser is ending there, if you were to actually zoom in, this is what it looks like. It's called the Great Rift of the Milky Way. It's this beautiful cloud of stars, billions and billions of stars that you can't resolve individually with your eye. So it just looks like this halo of light. And then these very dark patches that are caused by dust. So there's an enormous amount of dust and gas in our galaxy, and that causes what we call extinction, or dark clouds that eclipse the light behind it and cast shadows back toward Earth. So what you're actually literally seeing are shadows cast back toward Earth by these clouds of dust. So if we were to actually zoom in here using only real data, I can show that to you right now. So this is a zoom in. Every single image you see here is real. Every single little speck of light you see is a star in our own galaxy, billions and billions of stars. And remember that we think that more than 50% or more than half of all stars in all galaxies have planets circling them. And for those stars that have planets circling them, most of them have more than one planet. So just imagine the number of planets in our galaxy alone. There could be up to 10,000 advanced alien civilizations just in our galaxy alone on a pure numbers argument, on a pure statistics argument, right? There's no science fiction involved here, right? It's absolutely possible. So if we zoom all the way in toward the center of our galaxy and take the highest resolution image that we can take, that's why these stars in the very center look so fuzzy and blobby. It's because they're so far away, right? They're about 30,000 light years away in the center of our galaxy. If you look at this one star over the course of a decade, it's circled in red, it's just a little faint blob, it's called S2. You see that star orbiting something, right? So it's moving around and we don't see the thing that is moving around, right? There's some force, or some gravitational anchor that's at the center of that star, or the center of that star's orbit, that's causing it to orbit something. So does anyone know what that might be? It is the supermassive black hole in the center of our own galaxy, right? So we think that there are supermassive black holes in the center, in the hearts of every galaxy, certainly every massive galaxy. And these black holes can weigh or have a mass that is millions of times to billions of times more massive than our sun, right? So the supermassive black hole in the center of our galaxy, which is called Sagittarius A star, is about 4 million solar masses. So you take 4 million suns and cram all of that mass into actually a really small volume, right? So here's a question from the book. We go into a lot of detail of in terms of this answer, so I'm not going to give all this detail now, but how big is a black hole, right? And in the book, we ask, do you think it's the size of a pea, or the size of a house, or the size of a planet, or the size of a solar system, or a galaxy, right? And the answer is a black hole can be any size, right? A black hole is nothing more than a mathematical construct. It's a piece of matter whose mass density, or the amount of mass per unit volume, is so high that you have to draw what's called a mathematical horizon around this object, meaning the escape velocity from that piece of matter is so great that not even light can escape, meaning the escape velocity is greater than the speed of light. So that means that you could turn Earth into a black hole. You'd have to take the entire Earth and squeeze all of that mass into a volume the size of a pea. So if you squished Earth to the size of a pea, Earth would be a black hole. A black hole can be as big as a pea. An Earth-massed black hole would be as big as a pea. Now, the black holes get larger as you cram more mass in there. So the supermassive black hole in the center of our galaxy, this 4.6 million solar mass black hole, is about 17 times larger than our sun, right? A billion solar mass black hole is about the size of our solar system. Okay. So this is what a black hole would really look like if you could get into this impossible alien spacecraft and fly really, really close to the black hole and have, million SPF sunscreen and the world's greatest sunglasses and be able to survive against being vaporized within an instant. And if you could get this close to a black hole, this is what you would see, right? You would actually see blinding white light in the moment before your vaporization, because of all the radiation. But in principle, if you could survive, this is what you would see. Now, this is an artist's rendition. This is a painting, right? So keep that in mind. But what a black hole really looks like is this dark horizon, which is called the black hole shadow. And around it would be this warped halo of this, or ring of light. And that light is from the last photon orbit, or the last orbit of light, that is the doomed particles of matter that is spiraling around this event horizon, emit an enormous amount of energy that we see in the form of light, right? And this warping effect that you see is something called gravitational lensing. The black hole is so massive that it literally warps the fabric of space-time itself, and it creates this beautiful halo effect. So you're actually seeing the disk of matter that's spiraling around the event horizon like a pancake. And you're seeing the back side of the disk of matter, called the accretion disk, that gets warped and lensed in a ring around the object itself. So if you have more questions on that, and I'm sure you do, one could talk for hours about what a black hole would really look like. Please do ask in the chat and maybe we can get to it, but also check out the book. We have a much more detailed explanation. But the answer to this question is, how big would a billion solar mass black hole be? It'd be about the size of our solar system, right? So that's huge, right? But it's also kind of small compared to the vast cosmic scales that we're talking about. Now, I can actually now show you a real image of a black hole. A lot of people are not impressed by this image, but trust me, this is one of the most profound images in the history of science. This is a real image of a black hole shadow. We took our institute partially led this. The telescope is called the Event Horizon Telescope. It's a network of antennae all around the world. So we use the Earth as a large telescope in a way to image the supermassive black hole in the center of a galaxy 55 million light years away. We call it M87. This is what that black hole looks like, right? So the real black hole shadow is this dark void in the center. And what you see around it, this apparently like blurry ring of light, is that same halo that I was showing you in the image. But this is an actual real image. So this is an actually just jaw-dropping result that all of this theory finally was culminated in this decades-long project to image a supermassive black hole, and we saw the shadow, right? That is a Nobel Prize-worthy result. So just because this image looks blurry, keep in mind, it is one of the sharpest images ever taken. Now, this black hole is at the heart of a galaxy, right? So at the very center of a massive galaxy, much more massive than the Milky Way. There are about 400 billion stars in our galaxy. And it is at the core of the galaxy. So if you zoom way out, right, you see that this black hole is actually launching a jet of plasma that's traveling outwards. So this band of white light that you see here, this is a jet of relativistic plasma. This is superheated gas particles, right, that are shooting out from the black hole at near the speed of light. And it's creating this beautiful collimated jet, kind of like the, garden hose spraying water out in a really like sharp jet and powerful jet. And this jet is propagating, moving outward from the galaxy. And it gets so large that this jet here is about 23 petamiles across, or about 4,000 light years. And I'm not even showing you the whole thing, right? So I can zoom out further and show you an image from the Very Large Array, which is an array of radio antennae in New Mexico. This is what that jet looks like in radio wavelengths, right? So this is 8,000 light years across. Keep in mind, 1 light year is 6 trillion miles. So 8,000 light years is 8,000 times 6 trillion, right? Now we zoom out even further and you see the entire jet in its enormity, right? 200,000 light years across, right? Just impossibly large scales. So this tiny little black hole at the center of this galaxy is powering these jets that persist out to 200,000 light years. To give you an idea of what kind of scale that is, this, by the way, are bubbles or sound waves that are blown into the gas that this galaxy is sitting in by the central supermassive black hole. So all of that, this structure that you see in this X-ray image, this is an image taken from the Chandra X-ray Observatory, all of that is actually driven. It's like a musical note that this black hole is playing into this massive halo of gas that this galaxy is sitting in. So this big halo of gas, which is about 200,000 light years across, if that were, say, the size of the, let's say the supermassive black hole, it's about the size of a solar system, right? Imagine it were the size of a grape, right? So the black hole is the size of a grape. Then the scale of the jets that this black hole has launched would be relatively, or in comparison, the size of the Earth, right? So there's just an unbelievable contrast in scale. These are relatively small objects that input an enormous amount of energy into their surroundings. So we're going to talk a lot more about scale as we move into the latter half of this talk. But this is that galaxy again. Look, I'm putting a scale here, 300,000 light years. It's just so impossible to imagine, right? We cannot comprehend these scales, and so they don't mean much to us, right? Oh yeah, 300,000 light years, big deal. I think it's, a really long trip to go to grandma's. Well, we'll talk more about it in a bit, but just keep in mind that it is okay to not be able to comprehend the scales of the universe, because I certainly can't.
All right, so for the next question, could a spider survive on the moon? So again, what makes this book so fun is the questions are from kids, they're random. And when we go to answer this in the book, we have some information about the anatomy of spiders. Some of our questions have had longer answers, but this one is a pretty quick one. Could a spider survive on the moon? No, it couldn't. By the time I read that question, the spider would be dead. So that's an easy one. No.
Yeah, we technically go into a little bit more of an explanation in the book, but yeah, no, that spider's toast. So look, kids ask great questions. There's a little bit of potty humor because we're getting questions from kids, and that's fine. That's funny. My daughter loves it. But it's actually a good question. What would happen to my pee in space? And there's actually really interesting physics involved. I'm not really going to go into it because we are short on time. We want to keep to 45 minutes because we know you're all busy and Zoom is tough these days, right? But what would happen to my pee in space? A long story short is that it would first boil and then freeze. So I'm showing you one of the few real images, a movie from the Space Shuttle Discovery in 2009. The Canadarm had a camera on the end of it, and it could actually witness a wastewater dump that was happening during this mission called STS-125, which I was actually present at. I was present for the launch of that mission. And so while they were in orbit, they dumped the wastewater tanks. And what you can see is the wastewater, kids, it's pee. It's really just pee. And some wastewater too, but it's pee. It's being expelled from this valve on the exterior of the space shuttle. And the water is immediately boiling, right? Because the pressure just drops to zero. And then these tiny little droplets of water freeze instantly. So what it creates is this beautiful mist or snow of pee that is expelled from the space shuttle. So we go into the physics of why the urine would first boil and then freeze, but it's actually a really good question. This image to the other side of the screen is actually an image of pee taken from the ground. So this is the International Space Station. So this is a guy named Jens Hackelmann in Germany. He took this image of the International Space Station, which is that bright dot there. And that plume that you see here is actually a wastewater dump. So it kind of looks like a comet. Yeah, it's actually just pee. Not all the book is potty humor, right? We have other really great questions. Are there clouds in space? We could give an entire day's Zoom lecture on clouds in space. But the short answer to this question is yes. Oh my gosh, there are clouds in space. Everywhere you look, there's gas everywhere, clouds of gas. These are images that I'm just flashing on the screen from the Hubble Space Telescope. This is the Carina Nebula, a stellar nursery where baby stars are being born. These are the pillars of creation on the left side of the screen here, and another nebula on the right. These are all images from the Hubble Space Telescope. Keep in mind the scale here, right? How big do you think our planet or our solar system would be on these images? If you're thinking that it would be really tiny, you're right? So the Earth would be smaller than the tiniest little pinprick that you can make on this image. I cannot draw the scale of Earth on this image because it's much smaller than a pixel on my screen, right? So keep in mind the scale. Many light years across these images are. But yes, oh my gosh, there are clouds in space. Clouds of gas are the ultimate fuel from which baby stars are born. And so these massive clouds of gas, which we call nebulae, are stellar nurseries. And these are the infant grounds in which stars in a galaxy are born.
So this was a fun question when one of my students asked this for the book. What happens if you're standing on the moon and kick a soccer ball? So I just want you to take a moment and think about the answer in your head. Because I even asked some students this year what they thought, and it was a really important question for me as a teacher because it got at misconceptions. This is not the correct answer, but I had a lot of kids say, oh, I bet you could just kick it really hard and it would keep going and going and going and going. But what I think was missing from their understanding is the fact that the moon does have a gravitational pull. So the moon is about 1/6 of Earth's gravity. So now let's imagine that you can kick a soccer ball really hard. So if you go to the next slide, Grant, this is the hardest recorded soccer ball ever in the history of Earth was 131 miles per hour, which is 0.03 miles per second. So let's imagine you're this guy, you're Ronnie, and you can kick it that hard. Is that enough to leave the moon's gravitational pull? It's not even close. To be enough to leave the moon's gravitational pull, you would have to be able to kick a soccer ball 1.4 miles per second. So picture 1.5 miles, about that from where you are right now, a speed of getting there in a second. That's how fast you'd have to be able to kick a soccer ball to have it leave the moon's gravitational pull. So what would happen if you kick a soccer ball on the moon? Well, you'd just be playing soccer. The ball would go a bit higher and you'd be kicking it back and forth to each other. But unless you had some super amazing, robo strong leg, that soccer ball would not be going off into space like a lot of kids had an image of.
So the book gets really deep into these really fabulous questions that students have asked, and we get into the most extreme sort of phenomena in our universe. For example, we have a whole question on if it can really possibly rain diamonds on Jupiter. Jupiter is my second favorite planet after Earth in the solar system. The answer, it turns out, might very well be yes. We're not going to really get into it, but long story short, please check out the book, because our universe is home to incredibly extreme environments. And one of those extreme environments is the center of a very, very, very massive gas giant like Jupiter, where indeed it can actually rain solid diamonds. So I'm going to kick it to Natalie. Yeah.
That was super cool. Thank you guys. I know we're kind of running out of time, but I really appreciate you taking the time to put that together. I could listen to you guys talk about this for hours. But all of you guys joining us today might remember that when you signed up, you were able to enter our super special giveaway just by submitting your very own space questions. We were so excited about the questions that we got that we've expanded it a little bit. So 5 of you are going to be receiving super special autographed copies of What Do Black Holes Eat for Dinner? I know we're getting close to 5:45, so if you guys need to sign off, that's fine. We're going to be showing this on our YouTube page. You will link to it on Facebook. You'll be able to find it. But I'm going to turn this over to Katie and Grant and let them reveal the big winners.
So our first winner, his question, this is Charlie K's question. What % of space has been discovered?
So Charlie, this is a really, really great question. And this is kind of where I wanted to end my spiel for the day, because we've been talking the whole time about how incomprehensibly vast space is. So the very short answer to your question is a profoundly small percentage of space has been discovered, right? What we know about our universe is so vastly outweighed by what we don't know. And one of the overriding reasons for that is because space is so incomprehensibly vast. So I know that's a really unsatisfying answer. What I did want to show you is a pretty cool movie. I like a lot of aspects of it. This movie is now, I think, about 10 years old, so it probably is in need of updating. I didn't make it. It's from the American Museum of Natural History. This is going to show you, with using real data, of course, simulated images, but real data, the entire known universe, right? So here's the Earth, right? And imagine that we are in an impossibly fast science fiction spacecraft that can go many, many, many thousands of times faster than the speed of lights, right? No spacecraft or anything could ever travel this fast, but imagine we're on this, spacecraft of the mind, and we can travel as fast as we want. So we're going to start at the Earth and zoom out and show you the entire known universe in about a minute. So here's the moon. These green lines are the orbits of artificial satellites, including the Hubble Space Telescope and the International Space Station. That's the Earth. The white line is the moon. So we're zooming out. So now we're 1 light second from Earth. There's the moon orbiting the Earth about 256,000 miles away. Here's the Earth in our spot in the solar system. So that line is the Earth's orbit. The other green lines that you see are the orbits of the other planets. There's Mercury and Venus and Earth and Mars and Jupiter and Saturn and Neptune. As we move out, we're 1 light hour away from the Earth now. We're still moving out. Now we're about 1 light day from the Earth, and you can just see our solar system getting smaller and smaller. And you can start to see the light of our sun in contrast to the local group of stars, right? So we're 1 light year from Earth, not even 4 light years yet, not even close to the closest star. Now we're passing the nearest stars. We're now 70 light years from Earth. This is that purple sphere is the most distant radio signals. Here's our spot in our galaxy. Remember, 200 billion stars in our galaxy. We're now 100,000 light years from Earth. These green spots now aren't showing galaxies, but they're showing the locations of all the known galaxies. So they're not showing the images of the galaxies itself. Just know that every little green dot here is a galaxy consisting of hundreds of billions of stars. All of these dots, as we move outward and outward and outward, is a galaxy with hundreds of billions of stars and even more planets, right? So this is the known universe. That hourglass shape is not real. It's because we can't map the regions beyond our Milky Way that are obscured by dust. So that's not the actual shape of our universe. But I wanted to end basically with this video for this question, because it does honestly try to answer Charlie's excellent question of what percentage of space has been mapped. And it's just a vanishingly small percentage, but that's a great question, Charlie.
All right, and our next question winner is Sarah G. Are wormholes real? Could they be used to send messages?
So Sarah, this is a fabulous question. And the answer is wormholes are mathematically very real, right? So they are a consequence of what we call the Einstein field equations, or something called general relativity, which describes the structure of space-time, right? That's a lot of fancy words, but basically there are mathematical possibilities that might actually manifest as real things in our universe. The problem is we don't really fundamentally know, and we probably will never really know for sure, right? We're probably not going to ever observe a wormhole. But a wormhole, also called an Einstein-Rosen bridge, is in principle a tunnel through the structure of space-time itself. And on one end might be a black hole, and on the other end might be a so-called white hole. But in principle, they could be used to send messages or information or even matter through the wormhole itself. But then there are a lot of like weird consequences of that drop out of the math. For example, if you were to enter a wormhole, and that wormhole were to move in space-time, then you would exit the wormhole at a point in time that is actually before you departed. Really, meaning wormholes would, in addition to being a tunnel through space, also be a tunnel through time. Yeah, things get really weird. Maybe we need to write a second book. I'm not sure, Katie.
I think so. All right, and winning question number 3 is by Chase B. What would happen if you got stranded in space?
Jace, buddy, like I don't really have a good answer for you here. I just have some bad news, right? If you got stranded in space, that's kind of the end. Yeah, space is really, really big. You don't want to be stranded.
All right, our next winning question is by Maggie. Is there wind in space?
So Maggie, this is a fabulous question, really, really probing. The answer is absolutely yes. This image behind you is actually an image of a wind from a galaxy called M82. This is a starburst-driven wind. A wind is nothing more than a large-scale flow of gas, right? So when you're standing outside, pressure gradients of the atmosphere of the Earth will cause a flow of gas from one region of the Earth's atmosphere to another, and that's why you can feel this fluid of wind or of gas moving across your body and rustling the leaves and everything. Well, that happens at effectively all scales in our universe, right? That's what's beautiful about nature, is that the laws of nature are so invariant to scale, right? They don't care whether they're happening in your kitchen sink or outside, blowing leaves on a tree, or on a galaxy-wide scale like you see here, right? So all of this structure that's in that gas that you see are real astrophysical wind, this bulk flow of gas. If I could not put the Earth or our solar system on this image, it would be, again, tinier than the tiniest pinprick. So this is a real image of a wind in space. Winds are everywhere in space. It's a great question.
And our final winner is Olive. With so many forest fires right now, makes her wonder, would a fire extinguisher work in space?
Yeah, really, really timely, Olive. These fires have been absolutely horrible in California, and we're thinking of everyone there. That's a great question. We could really only have a fire in space, like, for example, on the space station, because we would need to be in an oxygen-rich environment to allow combustion to happen, right? But imagine that an astronaut, heaven forbid, you definitely don't want a fire on the space station, right? In fact, there are many, many redundant mitigating systems aboard the space station and aboard the space shuttle to prevent that from happening, because you definitely don't want a fire, because it could spread uncontrollably very quickly in microgravity. But if you were to use a fire extinguisher in space or in microgravity in an oxygen-rich environment, one thing that would happen is firing the fire extinguisher would actually push you in the opposite direction. It wouldn't be that fast, but you would, to what's called conserve momentum, you would actually move in the opposite direction. So it kind of worked like a thruster, if you will. But yeah, in principle, if the fire were localized enough and you were to fire this fire extinguisher right at this this microgravity fire, it would probably do a lot of work toward putting that fire out. Now, a fire in the void, the vacuum of space, wouldn't really happen in the way we think. But you could still fire that fire extinguisher and it would act again like a thruster. If you've seen the movie The Martian, I think at the very end of that movie, the astronaut uses a fire extinguisher to move in space, or maybe he uses a hole from his glove. Or no, it's the movie Gravity with Sandra Bullock. She uses a fire extinguisher as a thruster in space, and it would kind of work like that, but it wouldn't really push you that fast.
Those were all really great questions. I know we're a little over for time, but I got 2 questions if you guys don't mind answering, just a couple more. So the first one is, where do things go when they enter the black hole?
So that's Katie. Do you want me to take this one, Katie?
Yes, please.
Well, so I mean, but really, this is a great question, and the answer that anyone with a straight face, being honest to you, would have to answer is we don't know. The problem is that once you pass this mathematical boundary called the event horizon, a lot of crazy things happen, and the laws of physics really, really do break down. And so the honest answer to your question is we do not fundamentally understand what happens inside of a black hole. We just don't. There's a lot of mathematical speculation you could do, right? There's a lot of weird consequences. For example, any particle that enters an event horizon, its so-called world line or its light cone is doomed forever to proceed ever closer to the singularity, which means that moving forward in space is equivalent to moving forward in time, and moving forward in time is equivalent to moving forward in space. That's a fancy way of saying that once you enter that event horizon, you can literally never escape. Nothing can escape, not light, not a hamburger or pizza, not information, and certainly not us, right? But the answer is we don't know what happens to something when it enters a black hole. If you might have seen the movie Interstellar, a lot of people thought it was a really weird ending when he goes inside the black hole and there's a bookshelf basically inside the black hole. But I actually loved it because frankly, our level of ignorance for what happens inside of a black hole is so great that it might as well be a bookshelf, right? So that's a great question with a very long answer and an unsatisfying conclusion, but that's a great question.
And of course, we'd love to hear more. Maybe one day in the follow-up. We'll see. If you
What do black holes eat for dessert?
Oh, I like that one.
Right.
I always love your desserts. If you shoot a bullet from the moon to Earth, how far can the bullet travel?
It would definitely reach the Earth. It would absolutely escape the surface of the moon, right? It would be fired at greater than the escape velocity from the moon. And the Earth is actually really nearby. It's only about 256,000 kilometers. And so, yeah, it would reach the Earth, and it would fall through the atmosphere and eventually hit the ground, or more likely the ocean, because most of our surface of the Earth is covered in water. So you'd most likely hit the ocean. I certainly wouldn't want to be on the receiving end of it. But yeah, it'd reach the Earth.
That's really cool. Awesome. Well, thank you guys. That was really great. I'm so glad you guys could join us. I really enjoyed the presentation, and I hope everybody else enjoyed it as much as I did. Don't forget to get your copy of Black Holes, or What Do Black Holes Eat for Dinner, rather. You can get that for 25% off and free shipping if you use the discount code that's on your screen right now. And definitely don't forget to check out our upcoming Tumbleocity programs. We've got a lot of great stuff coming up. And on October 2nd, we're going to be talking about the puffins off the coast of Maine. So hopefully it's just as exciting as this one. Thank you again, and I hope to see you guys next time.
Thank you all. We're so happy you
you.
came. Thanks so much. Keep asking great questions.
And for those of you who are still on, I just want to point out that we do have this is Barnes here. I'm also from Tumblehome. We do have a YouTube channel with videos with Katie and Grant and a whole bunch of other things that we hope you guys will check out. So when you get a chance, go on over to our Tumblehome Books YouTube channel and check out some of our other awesome videos.
Thanks all.
Thank you.
See ya, Katie. Thanks,
Bye.
Natalie. Thanks, Barnes.
Thanks,
Thank you.
everyone.